You know, it's just still.
You can just right click and open in a new tab.
Yeah, I never figured that out. Okay, so what do I do?
Huh?
What do I do
Right
again?
click and open in a new tab. Go back.
Right click here.
Not here. Go back. Go back to the page. The link you wanna open. Let's get started.
Oh, like down here.
Then right click. Open in a new tab.
All right.
I was trying to check.
Yeah, that works. All right, thanks. Yeah, I know there's some tricks in this.
Yeah,
I
if you
don't-
hold control and you click on it, it should.
Okay.
also work.
All right. All right. That's pretty helpful. Remind me that again. I'll forget that. You know, it's like you see me doing it again, just say it, you know. You can preface it with you idiot. You know?
We also don't know all the tricks. So
Yeah, but it's pretty frustrating when I know there's some tricks that I want to use and I don't remember what they are. It's like, but anyway, we got 1229. All right, so that can project. I'm gonna go on this thing. I got this Dubai thing kind of worked out. Apparently, so this I got from this kind of I don't know, I got it off some webpage. Oh, Libra text or something. They like, there's something like Wikipedia for, I think it's called Libra text, but it's the same thing as what's on Wikipedia. I think they're all copying each other. But anyway, I wanted to, because the question in this homework is like drive the Dubai function or whatever. So I want to do that. Anyway, so the heat capacity function, and that does that show up? It never seems to get the whole picture here either. I'll zoom out.
What equation was it?
The heat capacity equations and
Oh, there's a buy from.
yeah, by I don't know, do they call it approximation? It's like almost
Yeah, it
exact,
says-
but
Heat capacity and constant volume under the Dubai approximation.
oh, you mean in the paper?
Yeah, your
Yeah.
question says derive equation 3.
Wait, no, this is the Einstein one. It's 9 NKB E over T Dubai cubed. So this is the low temperature dependence, and there's this weird thing, this integral to it. So it doesn't have an exact form. And then we had, like for the Einstein, we had like kind of this part, like either the X is like E over KT or omega H bar omega over KT, however you want to do it. But anyway, e to the x over e to the x minus 1 squared, then times this thing squared through NKB. So it's got kind of this part, and it's got this part. And then it's got this 1 over t dependence, and there's no integral. So they're different, but they're kind of the same. So he says, he calls, in the paper, he calls this thing like W something. W omega, I guess, or something. It's kind of weird, but I don't think it's omega, but WE, maybe something like that.
It just says W.
Or he doesn't call it of anything. Okay, so just W. And then so that, and then he calls this thing W times X squared, like the argument of this. Because it has already this is already that X squared term.
Here,
E over KT.
it says it's the weighing factor W, and then in parentheses, it's HB over KT.
Yeah, so it's kind of interesting, like anyway, the weighting factor is the Einstein. And this is the Debye one, right? So like the Einstein is kind of in the Debye one, more or less, right? It's an integral, it's within the integral of the Debye one. So that's interesting. So that kind of tells you that maybe you could start with the Einstein and get the Debye. I think Wikipedia might do that. Like start with the Einstein and then just somehow plug it in to get an integral out of it. So Einstein's going to have a fixed, this energy is going to be the Einstein energy. And that's going to be like the Einstein frequency times Planck's constant. And that's going to be somehow related to the Einstein temperature, or theta D, theta E. It's going to be like the Einstein frequency. It's going to be H Einstein frequency over K. I guess it's going to be the Einstein temperature. And so in the same way, you have a Debye temperature is defined kind of the same way, except using this XD. So XD is the Debye frequency, which in this thing, they call it, it's this angular frequency times H bar. Right. X is that over K, yes, that by K. So that ends up being like a temperature too. I mean, that would be the Debye temperature. Anyway, so anyway, it's just this other thing, this whatever it is, Libra text, whatever. Let me get rid of that. But that's what we want to get, is to get this equation. So anyway, so got a bunch of paper. Right. So when you start out, he just defines some terms, right? So you have like the frequency, I mean the energy is H bar nu, and then that's it. But basically that's the same thing as H over 2 pi for the angular frequency, and that's the same thing as H nu, because the angular frequency is 2 pi times the frequency. It puts the frequency in terms of a full, like it's kind of a circular frequency, like an RPM kind of thing. So anyway, so that, but for this part, we're just dealing with this angular frequency. And then the angular frequency is the speed of sound times this wave vector, K. So it's the wave vector is a vector. And K is going to be, K is 2 pi over lambda, like the wavelength. So but it's got a direction to it. So now it's got a direction too. In other words, it's within a lattice. So there's an inverse lattice, like the Bravais lattice, but it's for the sound thing. And then K's positions along that lattice. You can think of K as a kind of a dimensional thing, but it's got units of inverse size. So it's inverse space. Inverse size, 1 over size.
Oh, okay.
So big K is small size. When K goes to 0, you're at infinity. So that's the point where when K goes to 0, that's the whole object like moving around, or else like pulling on the objects. That's the modulus. You get the modulus out of the whatever. analysis you're doing. I think the K versus frequency plot will give you the modular. The slope is going to be square root of K over M. The K would be like the spring constant of the modulus. Right, like when you plot so yeah, you have frequency versus K, and then when you get to 0, it's a straight line, and the slope of that is square root of the modulus, which is also called K, but capital K. In other words, that's the modulus of one atom, one atomic, between two atoms. What's kind of the spring constant of it?
Right.
So, and then divided by the mass of the atom.
So that's like for harmonic oscillation.
Yeah, but here this behavior for the Debye, it's going to end up being the sine function, and it'll be like this decay thing, right? So it goes to flat at 1, we're at A, like where K equals 2 pi over A, the lattice spacing, and then it's going to decay. And when you get to 0, which is infinity, and then it repeats itself on the other side. So it kind of looks like that. That's like that's a dispersion relation, or the Debye model. The Einstein model, you only have omega E, so it's just like constant. It has no, the dispersion relation is just there's one value of frequency, that's it. And so that's kind of the difference between the two. The Debye ends up giving you this dispersion relationship. And Einstein just gives you one value. Then you can actually measure. So you can actually measure the dispersion relationship, right? And you can do it spectroscopically. So from IR, you can get the, or you can do it with a computer program using density functional theory. So that's what this guy does. He uses this VASP code, which is density functional theory. And then he uses the projector augmented wave method, which is some kind of part of VASP. So this is like doing Schrodinger equation, but it's simplifying it because you can. It's basically an approximation of the Schrodinger equation. So you can use it to look at real material. Schrodinger equation, just look at like one electron or something. You get the electron cloud for one electron. This gives you like actually whatever he's looking at here, which is carbon, either in diamond or in graphite. And then he also does boron nitride, either in cubic or hexagonal. And then so he's going to get the dispersion relations here. So this is a frequency versus wave vector. You can see, well, they go to 0. That means that's the modulus. Those are acoustic phonons. Then the ones that don't, that's like the dielectric constant. So that's optical, right? And then, so it isn't exactly the Debye shape. It's not this sine thing from the spring where you add up the beads and you have the bead in the middle and the two side beads, and you can get this sine function for the. So basically, it's not the sine function, but it's close. You know, it kind of looks a little bit like it. These are actual experimental measurements, so it's going to. The sine function doesn't include like the atom moves and then it's within an environment of a crystal and whatever happens to it. You know, so basically this is a real thing. And then the Debye, that sine function is for this model of just coupled springs. And then if you didn't have coupled springs, it would just be a single value, the Einstein one. So Debye is significantly better at modeling acoustic phonons than the Einstein, which is just this one straight value. Right? But still, it's not perfect. So you need to either experimentally get these curves. So he's got experimental data, these little triangle things, and then he does this density functional theory calculation. That's the lines, right? And from that, he can get the density of states, which is kind of over here. So density of states means the probability of finding an electron at that frequency, vibrating at that frequency. In other words, the frequency is the energy, like h nu. So frequency is energy. So how does the energy dispersed over frequencies? There's going to be a certain amount of thermal energy dumped into the system. The system's going to bin it into its normal mode vibrations that it has. So everything has like normal modes of shaking, right? So if you can sonicate, there's a video on the line somewhere. Maybe it's in Wikipedia somewhere, but they show a droplet of water in a sonicator. And you think, well, a droplet of water is just going to like do nothing. But if you put it at the right frequencies, it takes all kinds of forms, right? So it's got normal modes. Even a droplet of water has a certain shape and it vibrates due to its modulus in certain directions better than others. And the crystals have that kind of behavior too. Like this, the normal modes of things like if you put a coordinate system on it, no matter which coordinate system you put on or which direction north and south are, it's still going to have those same modes. So they're like they're indeterminate. What are they called? For matrix math, they're called indeterminates or something. Not determinate. In something. Anyway, it's the things that don't change no matter the coordinate system notation. So you vibrate the thing, it's got certain vibration. So a bell would have like a vibration like that kind of. That would be the normal mode for a bell. And it's got, then depending on the shape of the bell, it's got all other kinds of weird vibrations that give it its tones. It's not like a computer simulated sound. It's got all this other richness to it that comes from the shape of the bell, right? So you get other normal modes in it. Okay, so that's what this deal is like. So you can have things that acoustically vibrate like that, or you can have things that vibrate when an electromagnetic wave comes in. So if you take an electric field and put it on the material like NaCl, and then the Na goes one way, the Cl goes the other way, plus and minus. The electric field's oscillating at a certain frequency, and the material is like shaking, right? Kind of absorbing that energy. And it's only going to absorb in certain frequencies, and that's the spectrum you get, like from IR. So IR is going to be the bond vibrations. Basically, you're going to have various different kinds of vibrations, depends how many atoms there are and the geometry of the structure and things like that. So basically, you're going to get vibrations due to electromagnetic waves coming in, or you can get vibrations due to acoustic waves. They're going to be around the same energy, right? So they're in the same spectrum of frequency of energy, right? And all these add up to give you the heat capacity, because the optical vibrations and the acoustic vibrations, they can both be excited by temperature. So this kind of plus minus vibration at NaCl, temperature can make them do that because the atoms are dancing around all the time and they find a normal mode where they like to shake. Plus minus, its polarizations involved, basically it's still shaking. So still absorbing heat into that vibration. They can also vibrate due to the acoustic kind of vibrations, like due to actual motion of the atoms. Like you hit it with a hammer, it shakes. Hit the bell with a hammer, whatever. Right? So, okay, so those are the two kinds of, there's like optical and acoustic vibrations that are happening. He can calculate those with his density functional. So he does actually the wave equations for atoms inside carbon, inside diamond lattice. He does the wave equations for carbon inside graphite sheets, and they can get these. You can get these distributions of how it absorbs the energy, like when you throw thermal energy in, how is it distributed, right? And the part that he thinks is interesting is that you can see that with diamond, there's kind of like one big peak, right? And then with graphite, it's got this valley in between these shallower peaks, right? And it turns out when he runs his density functional theory calculation over different temperatures, that so at low temperatures, you excite the low frequency. So low temperatures, low energy, KT's energy, H nu's energy. So low temperature, low frequency. You get the higher temperature, you get a higher frequency, then the peak of the Einstein thing fills up. Then you get that will be the heat capacity changing with temperature is going to be kind of how that fills up with energy. How it absorbs energy as a function of changing the temperature. So what's the difference between these curves in terms of area? That's how it's sucking up energy to turn it into vibrations. With graphite, this part is never excited, like the mountain range off to the east or whatever it is. The mountain range over to the west gets excited right away and then doesn't change much, and then boom, you get this thing. So that means that something happens with graphite when you get around 1,000 degrees Kelvin, that it changes from not as much as diamond to like kind of more than diamond. Right, so he sorts that out from these curves, and then he shows in those curves, he calculates the heat capacity, and he says, yeah, there's 1,000, it's like right here, and yeah, the diamond gets a higher heat capacity when that transition happens than the graphite. And the same, so it's kind of subtle for this, but it is kind of odd that diamond, the way you tell it's a diamond, like versus glass or whatever, or cubic zirconia, is you put it on your lips, and if it's cold, then you know it's diamond, and if it's warm, it's cubic zirconia, right? So, but if you did that at 1,000 degrees, that wouldn't work. Of course, your lips would be fried. But basically, you know, that's kind of the idea here, is that the main feature of diamond is it's cold and it changes when you get to 1,000. And so he also says some interesting things like the graphite. So the reason it has this low end stuff in graphite is because that's the graphite sheets, aromatic sheets that are conjugated, right? So they're stiffer bonds than the covalent bonds in diamond. But they have this like sliding vibration, like that's why graphite's like a lubricant. You can use it as a dry lubricant, right? So, and also why it's not like as hard as diamond, say, right? Diamond's supposed to be the hardest thing. So anyway, so these lower vibrations are that sliding business. It makes it a lubricant, and the upper ones are the in plane vibrations, are the really strong bonds, covalent. So it's a conjugated, means that you have double bond, single bond, double bond. That means the electrons within that are free. Those are pretty good bonds because they can, kind of deformation you make to it, it can adjust, like it can move the electrons around. So it's a stronger setup. It's like it reaches like a sweet spot, you know, that when you have an aromatic rings and graphite's going to be like connected aromatic rings. So the whole thing's conjugated all the way across it in any direction within the plane, right? So right, when you reach the high temperatures, you excite those really strong excitations or vibrations, and the in plane vibrations, and then that's why the diamond doesn't have that. It's just got covalent bonds, straight covalent bonds between the carbons. It's kind of interesting, you know. I mean, if you're interested in it, if you're doing work with nanotubes, and it should be really interesting. You know, if you just in generally kind of looking at it, it's kind of interesting. Diamond's always interesting, I guess, for some reason. But wait, he gets the same deal with this cubic boron nitride and hexagonal boron nitride, that the density of states. So this looks a lot like diamond. And this is also cubic system, is diamond cubic, right? And this is also cubic. And then the hexagonal, I guess, looks like a benzene rings hexagonal, but it's not really a hexagonal crystal. But so that also has this valley thing, and then a excitation at the high end. And for that system, because it's, I guess, because it's a pretty much larger peak here, then he sees a much more dramatic effect on the heat capacity. Like he sees a complete change in that. It's pretty drastic. So anyway, that's the point of this paper, more or less, in a nutshell. But anyway, so I'm asking you to derive this equation, number 3. So I'm going to do that here. Like somewhere here, I say like get equation 3. So that's what I'm going to do before I run out of time. So anyway, so forget about this. Just define the terms, and then K is 2 pi over lambda. And then we have this Bose-Einstein probability, like number at some energy E is 1 over E to the E over KT minus 1. So that somehow we got that. That's just a probability, right? So that's going to be the probability at some frequency of occupying a state of energy E, which is E is H bar nu. Right. So that's a frequency distribution of the electrons in the system. Yes, right. So anyway, so you're going to have, so the point of this thing is to have right, and then there's like an inverse space. So the idea is you're going to have this in inverse space. You can draw a lattice of your this. So this is going to be like Kx, Ky, Kz. So each of these are like 2 pi over lambda, over 2 pi over some number, some dimension of size, right? So you can have, if you say you have so if you have, say you have a bunch of beads and then the highest frequency vibration is going to be just one bead vibrating, right? And that's going to be, so that would be actually the largest size in this kind of Boolean lattice I made. How do we spell Boolean? I can never spell that. Oh, sometimes there's 2 L's and an I. That's 3 L's with it. Right. That's like a Boolean lattice, so that the largest size has to do with the smallest size in real space, because it's 1 over size. Right. And the smallest size would be the largest size. So anyway, this size volume of this lattice is going to be kind of based on this Boolean size. So it's going to be actually the A spacing of the atoms in it would be that would be the largest frequency that you get. This Debye frequency, that would be the highest energy, the vibration you need. So you think about, if you're shaking the stuff, it's going to be easy to shake the things that are big and harder to shake the things that are so small. That's the idea. So you get to these small things and it's a high frequency, high energy vibration. That's the highest energy vibration you have. So anyway, the Boolean zone has a volume, so you can end up with the number of modes, capital N, is going to be the volume. So the K of this Debye size, which is going to be, again, K is 2 pi over A. So this K Debye is 2 pi over the lattice spacing, or whatever the spacing of the dots are that you're looking at, like whatever. So you have the wavelength. When the wavelength matches the size, you're at BD, and that's 2 pi, 4/3 2 pi KD cubed. So it's an inverse space volume, right? So that's going to be, well, anyway, the number is going to be that divided by 8 pi cubed divided by the actual volume of the system. So the volume of the system comes from 2 pi over L, the whole system, cube. Right. So this would be the smallest inverse size, and this would be the largest inverse size. So that the ratio of those two gives you the number of modes of vibration that you have. You could write this in real space if you wanted, like it would be L cubed over A cubed, but it's done as an inverse space. That 2 pi over L cubed is like 8 pi cubed. Let's see, how did I get this over the volume? Oh, that's just the volume would be L cubed, and that's just 8 times pi cubed. Right, so 8 pi cubed over volume gives you the K vector for the smallest point in the thing. So you can't actually go to 0, you go to the total lattice size thing. And if you normalize, take the total lattice size, which is a small number, even though it's the biggest size, the biggest real space size, and then anyway, that would give you the number. That ratio will give you this number, like how many modes you have. Modes of vibration. All right, then this KD I got is 2 pi over A. You could also say that KD is this frequency D over the speed of sound, because that works out. Like if you have the wave vector, so the speed of sound is meters per second. You divide by lambda, then you get how many lambdas per second, or how many, in other words, the frequency of the wave. And if you do 2 pi, it'll make it like a fraction of cycle, like RPM kind of thing. So basically omega VSK, omega is VS, velocity of sound times a K vector, right? So you can say the KD, the Debye K vector is going to be the frequency divided by the Debye frequency divided by the velocity of sound. And the Debye frequency is like the energy by H. So everything kind of should more or less be definable in terms of everything else. So then once you have the number of modes and KD, they're related to each other. So you can rearrange that and just get that KD, so it's cubed. So you're gonna end up with 1/3 of all this other junk, like the 4/3 and the 4/3 and the 8 kind of cancel out and end up with 6 pi over pi cubed gives you pi squared. And then the number of modes divided by this volume, the volume of the Bravas lattice kind of. In real space volume of the thing, of the unit cell. This is a unit cell. The unit cell volume. All right, so you can define this KD in terms of some things that you could theoretically know. So, and then once you have KD, then you can write that this frequency, the Debye frequency is going to be KD. The Debye frequency is KD times the velocity of sound. So that's the same thing, 6 pi squared n times this volume of the unit cell, 1/3 times the velocity of sound. And then you can rearrange, from that you can rearrange to get the number of modes. So the number of modes in terms of the Debye frequency, which, so you can get the number of modes, it's going to be the Debye frequency divided by the speed of sound, which is here, cubed, times this volume of the unit cell, divided by 6 pi squared. All right, so that's kind of, most of this is just defining terms. It's just defining what the terms are. So it isn't, this is actually not that, it's just a lot of terms that need to be defined. But so anyway, then you have the Debye temperature is going to be the energy over Boltzmann constant, and then because temperature is missing, and that ends up being the Debye temperature. Right, so we had like X is going to be TD over T, so that's going to be H nu omega D over KT. Right, so that's where the Debye, if you have T, then this Debye temperature, which is also just called theta D, usually, right? So that's the Debye temperature. The Debye frequency gives you the Debye temperature 1:1. And if you plug in that frequency, then you get the theta D is H bar Vs over the Boltzmann constant times the cube root of that thing. Cube root of 6 pi squared n over the volume. So the reason to go through all these is because then you can, is so that you can plug those in after, right? So if you want to know what's the internal energy, then you say, well, the internal energy is distributed in space by this density of states, which we had plots of, right? So density of states is going to be a graph versus frequency, tells you how the energy is distributed, right? So if you integrate over the total internal energy is going to be the density of states integrated across all frequency, and then times the probability that you have that energy, n omega, which we had somewhere here. N omega is going to be this guy, like n omega is 1 over this Bose-Einstein function, 1 over e to e over kt minus 1. That's an omega. And then the density of states you need, and then h bar omega, like that, right? So this guy is going to be 1 over e to the e over kt minus 1. And then the density of states, let's see, look at that. The density of states is, let's see. The density of states you get from, okay, so the density of states is the derivative of the number, which we got, versus the frequency, which we have that whole thing. So we have that somewhere here. I have it right here, right? So the number, those are the frequency cubed, right? So the dm omega is going to be omega squared, and then divided by Vs cubed times this volume thing divided by 6 pi squared. I can plug that right in here, plug that in here, then I can have an expression for u from that. So u, and just the derivative of u is what we want. So u integral, and you're gonna integrate this up to the So once you get to the Debye frequency, you've filled up all the energy. So that's the most energy you can take. Like the smallest, just the A things shaking, and like just sine wave with just the atoms. That's the highest energy that thing can take. Can't take any higher energies. There's no point in integrating energy up any higher. That's the end of the story with the Debye model. Right, so you go 0 to omega d, so that allows you to kind of solve it, right? In other words, you end up with an integral form, but it kind of lets you solve it. So d omega, this volume of the unit cell, omega squared, then 2 pi squared vs cubed, and then this Boltzmann factor e to the h bar omega kt minus 1, that, and then let's see, I got another h nu from where? Dn is omega squared v vs cubed 6 pi squared 2 pi. This thing. Oh yeah, there's an h in here because you have to put in the energy that you're integrating. H bar nu. Yeah, that's good. That's helpful. All right. So this is kind of written for 1D. So you have to do times 3, and then in this Libra text, whatever, he says that with acoustic modes, you have 1 longitudinal and 2 transverse. So you can think, I think this is, anyway, for 1D, you would have like, so you'd have like clustering along the line. So that would be a longitudinal vibration, like an accordion kind of vibration or slinky vibration, like how can, and then you could have like X and Y vibration. So I guess that's where the 2 transverse and 1 longitudinal equals 3 vibrations. They all have the same behavior in this model. So it's just going to be a 3 out in front of this. So you end up with this, the internal energy is 3 VH bar, 2 pi squared VS squared cubed, right? Same thing as that. That none of that depends on frequency, right? And then integral 0 to frequency Debye d frequency, and you have 1 frequency here. So I took the h bar out, and I have 2 frequencies here. So I have frequency cubed, then divided by the Bose-Einstein thing, E h nu over kt minus 1. Right, that's the internal energy. So you think that, okay, all I have to do is take a derivative of that, and then I got then I'm done, right? That's it. But turns out like that integral, like, isn't that easy to do? Like, I mean, the derivative of that integral isn't that easy to do. Oh, you substitute in that xd is td over t for that thing, and x equals h bar nu over kt. Right, so the t comes from here. Td is h nu d over k, and then that gives you xd. So you get like the integral to, so you can change that to the integral to xd. So that thing becomes that I can just rewrite it 3 over 2. This is that total volume of the unit cell, h bar pi squared vs cubed, and then integral 0 to xd replaces omega d dx, and then it's going to be x cubed over e to the x minus 1. And then let's see, is it, I think that's up here. There's also a kt over h bar that comes out of that. Kt over, oh, there's a kt over h bar, and there's a kt over h bar cubed here to get the x cubed. And then that gives you t to the 4. T isn't part of this, it's a frequency integral. So that t to the 4 comes out front, t to the 4. And then you have this k over h. Somehow you get t to the d. Let's see what do I end up with. end up with t to the 4, but it's t to the cubed over td times t. And then kb 9n, because it was 3 times 3 for the 3 directions. And then the same integral 0xd x cubed over e to the x minus 1 dx. So that's kind of the form that you see, like whatever he gives for the he doesn't give this, but this is the form for the internal energy. So you need CV is going to be du dt constant v, right? Which means you have to take the derivative with respect to t of this thing and xd. So xd depends on temperature here somehow. Let's see. xd is h bar omega d over k. It doesn't depend on temperature. Oh, but the xd doesn't depend on temperature, but this guy x does depend on temperature. So x is h bar nu over kt. So there's a t in this kind of weird integral equation, right? Making it impossible to solve, as far as I can see. So they call this integral d3 of x, the third Debye integral, which you can find on the internet. I think maybe just d3 of x might give it to you. Nope. Oops, had it there for a second. Debye integral. Generalized by integral. So it's like a math function at that point. There's actually a wiki page for this. Let's see. Debye model. Debye model. Within that, find D3. Oops. Maybe down here somewhere he says D3. So, and then, all right, so supposedly you can look up D3. Oops, where? Why am I blind? UDD, it's, oh, D3, the Debye function. Didn't I, oh, I put in Debye integral. So that's the same thing, right? And so the reason he wrote the Debye integral or function is that you can do the derivative. The derivative's like right here. That's the answer, right? That's the, you want to do the derivative of that with respect to t. X is kind of t. You can do dx dt because x is 1 over t, sends it minus 1 over t squared times the constant, right? So you could do that. If you knew the derivative of Debye integral, you could do it, kind of. But if you go to try to do this, I mean, it doesn't work out to the answer that you want. So I don't know how to do that derivative. If you can do that, it's probably some extra points on the homework. Or you can just say you use D3 and it works, I guess, you know. But it's disappointing, but that's how the world is here for me right now. But so the final answer is going to be this this thing, like supposedly the derivative of that thing. So I think that if you do the derivative, I would do derivative by parts. I could do derivative of this gives you like t squared 3t squared times that integral thing, plus this thing t cubed whatever over td times the Debye thing, which would be this thing, which has to have an x out front, and then the solutions on that web page. Then you get another 2 terms from that, because that's got like b and d in it or something. B of x, d of x. So it's not just the one thing. So that doesn't look like this, which is cv equals 9n kb t over td cubed integral 0 to xd. You can kind of see where it comes from, but it's not really very rewarding. E to the x minus 1 squared, especially because like this part with x squared is the Einstein function. That's the Einstein heat capacity. So it's already got the Einstein built into it. It's got an extra x squared here. So if you look in our paper, wherever that is. So he's got WH, that's the Einstein function. That's Einstein for heat capacity. Then he says that times this gives me CV, that integral gives me CV times the density of states. But why that weighting factor? I think it's just backwards. Like he had this answer and he backwards did it and then figured out that it was the density of states times that. So that thing must be a weighting factor. That's my impression. Because the actual weighting factors is Bose-Einstein, this exponential -1 term, 1 over that. So who knows? I don't exactly see how to do it. That last step, which is the most important step, I can't do. I tried doing it, I gave up. I did try to do it like a couple different ways. I tried doing it without the Debye thing. The Debye thing should have it solved. So you just plug and play. But if you plug and play with his function, that didn't work for me either. So I tried it 2 ways. One, just straightforward, just do the derivative of the integral, like derivative of that, then derivative of this thing. And the other way is use that Einstein, that Debye function. There's 2 ways. There might be other ways to do this, or you can just derive this from a totally different way. Like if you go back to this web page, he's got like 3 ways he derives it. One is basically the same thing as this Libra or whatever thing. So Debye had some weird stuff, like supposedly, right, first off, he was the head of the institute in Berlin for physics, like the top place in Germany during World War II. Then he left Germany, put all his money into gold. He made gold coat hangers. And he left Germany with gold coat hangers. And then he went to like Cornell with his gold coat hangers. And he had all the money he had was in coat hangers, like to get out of the Nazi Germany. But then later on, is a Dutch guy, right? So later on, they started saying about 5 years, 6 years ago, they started saying oh, he actually was like killing Jews or something, like when he was in Berlin, and then he just got out. Maybe he got sick of the killing or something. So he was kind of so his whole name was kind of trashed with this association with the Nazis while he was in Berlin. Pretty hard to tell. Anyway, he's still like a genius. He's still the stuff is and this is just one of the things he's done. I mean, actually, this heat capacity is the most famous thing that he did, but he did so many other things too, like a lot in polymers. He did the polymer scattering function, things like that. So, but he did a lot in colloids, the diffusion equations, surfaces. He's got so many Debye equations. I get dizzy looking at him. So, and it's all like Einstein, everything's so complicated. It's too complicated. And Debye, everything is really down to earth. It's stuff you really need to know. So, like a charging Debye Waller factor, Debye colloid, like for interfaces for charges, Debye screening. He invented he invented screening. He invented a lot of things. So anyway, he is a great guy scientifically, but he does have this kind of thing attached to his name now about the Nazi business. So anyway, so yeah, they derive it. This is kind of the way I just went through. So here's the thing. Oh, all you have to do is take the derivative of that and get CV. So they say D3, then that would solve it. I mean, you're allowed to do that too if Wiki can do it. But basically it'd be nice to see somebody actually solve this thing. Then there's Debye's derivation might work. Seems like I did this before and it worked out. And then so there's 3 derivations here. So one of them should be possible to do. I didn't have time to kind of go through all of them. And then the limits of it. So low temperature gives us T3. And at high temperature, it gives back the Dulong-Petit thing. I mean, because
GPT could do it.
Huh?
You think ChatGPT could do it?
Maybe. It might, but it might be wrong. Yeah, it might be wrong. I've been using ChatGPT a lot though lately. But
You have been?
yeah, just question about this or that. It can be wrong. I mean, you have to be kind of careful. Actually, you have to kind of roughly know the answer before.
to know if it's wrong,
Yeah, so it's a little bit of a catch-22 to it.
right?
I forget what, oh, I'm not sure if it was this class, or I think it was that other class, and someone said like, oh, we got these answers from Chat GPT. Yeah, it was just like calculate like for batteries, the C function or something or other. Just a bunch of battery things, you know?
I've
And like the
asked it-
first one was perfect. Yes, that's right. Chat GPT got it right. But it was of 5 questions and the other 4 were completely wrong, you know? So it's like 0, 0, 0, 0. You got 20.
it'll introduce like seemingly unrelated terms somehow. From whatever.
It just got it wrong. Like it was just flat out wrong, you
Yeah.
know, like thing. And it was, I think it was partly like the question you give it, then it gives an answer kind of related to that question. If you didn't phrase the question right, it's not gonna give the right answer. It's useful at times. If you have no idea at all, it gives you a rough idea, but then if you kind of back check it,
Yeah,
that's a good idea.
there's a section in the, on the website where you can give it your own notes, kind of your own parameters of what types of answers you're looking for.
Oh, yeah.
Um,
Yeah, I just write a question. I haven't gotten that much into it. I know that you can use it. Plus, I think I'm just in the part where you get just a paragraph answer, and I think there's some other way if you pay or something, you get longer, more elaborate answers.
Yeah, well, you can give it instructions like, don't give me long paragraphs, give me like.
One
more
word, one
equations.
sentence. Oh, just give
Yeah, or
equations.
make it shorter.
Yeah, all right.
Anyway,
Yeah, I think it's pretty powerful. I'm in favor of it. You know, I'm just saying like there's some little twist to it.
yeah,
Like they say Wikipedia is dangerous, but actually Wikipedia is almost always pretty good, you know. Only a few cases. Actually, I corrected a wiki page the other day. But it's like that's pretty rare, you know. Like they've already been read by so many people and you can fix it yourself. So, but you know, anyway. So yeah, there's 3 derivations here. If one of them makes sense to you, then use that and I'll give you some extra points. Point out that like say something like, oh, you idiot, you couldn't solve this in class, and like I just did it. It was so easy. Ha ha ha. Then it's probably like some points there. So anyway, that's that business. So yeah, this homework though, let's see. So he's got the first thing he's talking about diamond, like he talks about hardness and stiffness. This is like a recycled homework in 2021. So, but I thought it's good because we did Einstein. This is Dubai. So it's kind of useful. But anyway, for some reason I thought it was important to say like hardness and stiffness. So, I mean, hardness and stiffness is modulus. Hardness is like, does it scratch the thing? Like if you take diamond, it scratches glass. Diamond's the hardest thing. It'll scratch actually anything. So, and then like if you wipe your glasses with cotton, so cotton is harder than plastic and glass, I think. So if you wipe your glasses with cotton, it'll scratch them. That's why you need to use some weird cloth, polyester or something or other.
does hardness have like SI units? I know it's like Rockwell senior.
Yeah, the Rockwell thing is like unitless, I think, and it depends on the class of material, so you get different numbers. So
Says SI unit of hardness is newtons per millimeter squared. So I guess it's like a force per area.
like a drag coefficient almost or something. It's like,
That's an arbitrary units.
Right.
all right. Anyway, he talks about hardness because he's talking about diamond. It's the hardest thing. So he says the hardest common material. Maybe there's something harder than diamond. And stiffness is the modulus, you know, so I mean, it's kind of the Young's modulus, more or less, but you might think of it as a kind of a torsional modulus even, but I mean, in fact, he says like stiff or flexible. So flexible, when Young's modulus is just a tensile measurement, and flexible kind of makes you think of a torsion measurement. So it's probably the stiffness probably more to do with the torsional modulus. I mean, but everyone says just Young's modulus. And then so hardness doesn't really have anything to do with heat capacity, right? Because basically heat capacity, you're talking about the the bond between the atoms, like in a tensile measurement, more or less, or some other kind of thing where you're, well, I guess if it's a transverse vibration, it's like actually is like a torsional kind of thing. But it doesn't have to do with hardness at all, because it doesn't have to do with like scratching things. I mean, there might be a relationship between hardness and stiffness, but basically the capacity calculation is going to give you a modulus of stiffness. I mean, it's probably this question has no importance whatsoever, you know. Then the optical and acoustic, I think I talked about that already. And oh, well, this is interesting. He talks about this at some little bit of length, a couple sentences, but so the acoustic phonon, so if you calculate the heat capacity using his density functional theory thing and his whole routine to get the density of states, then you get then he's going to get the entire, like the heat capacity is going to be the entire optical and acoustic, not just the acoustic. And only the acoustic relates to the stiffness, right? Because the optical isn't going to make any difference for stiffness, because you're not actually, anyway, acoustic is mechanical and optical isn't. So you're not going to get a modulus from an optical part of the heat capacity. So heat capacity takes both optical and acoustic. Stiffness is just acoustic. That's the bottom line. Then vibrational frequency is proportional to the square root of stiffness and harmonics. So this thing we derived in class, right? It's just the harmonic oscillator thing, wherever that is in the notes. Like over here somewhere. Like one of these things. I mean, that's the equation here. That came from back here somewhere. So from that, you can theoretically calculate the tensile modulus of the material. Early on. Oh, here, it's up in this corner. So slide 14, it's like do a force balance. So spring constant, mass times acceleration. Plug in a sine wave solution to it for the speed thing. And then if you just, so you have sine of, and then the second derivative is also sine, so sines cancel out, you end up with the frequency. And then if you do derivative of sine, you get, with respect to time, the frequency would come out as a prefactor, so you end up with like frequency is a square root, and it's going to be squared because it's a second derivative. So that just that thing, just plug this into that, do the second derivative, and you'll get this answer for what frequency is. So if you have so you can get and if you do this whole solution, so then if you do this whole business of the sine thing, you find out that whatever the bead thing is, the bead thing, and a lot of junk here, the beads, and then here you end up with you solve that, you end up with this cosine function, and then plugging that back into that equation gives you this business. That actually, oh, this is probably the best way, because then it just tells you that in terms of wave vector, you get the 4 times the modulus of the mass. If you do this plot, and at this low end, you can get the modulus. Low k end. And he's got in this paper, well, he gives it the by temperature, but you can just plug that in, or you can get it like these plots show the modulus. So each of the different crystal, usually these would have like crystallographic planes associated with them. So, but this is different moduli in the different crystallographic directions. So you get the modulus from the acoustic phonons, not from the optical. So it's going to be just the slope when you get down at this low end. And that slope is going to be like is gonna be 4K over M, right? It's gonna be like this thing. This thing goes to, so sine at low angle becomes the argument. So it's gonna be 4K over M times the wave vector. So the slope, you remove the wave vector part because you're doing the derivative. And then it's gonna be the lattice spacing over 2. Somehow that should give you modulus, like frequency. Somehow the units of that should end up being modulus. You might have, it's going to be A, so you have to convert it to per, what is it? It's just going to be force per area, but you need, A is going to be in nanometers. You're going to have to convert that to whatever units of size that you want. It should work out. The Q is inverse size. This is size. That's unitless. K is the modulus over mass. That square root of that ratio should give you frequency. Somehow you can get modulus out of this. I think you have to figure it out. That's the bottom line. So how do you get the bulk modulus from that tensile modulus? And then it's possible to do it. Calculate the Debye stiffness. How does it compare with the actual stiffness? So I think he gives the stiffness for diamond or something like the modulus of diamond, but you can, but here he says, like, I think he even gives the values in here somewhere. Calculated, what's this? Table calculator lattice constants. Oh, well, anyway, you can calculate it. If you can't find it in here, you can just Google diamond modulus or something for that. Hopefully that works out. And then he says the heat capacity of graphite becomes smaller than diamond at 100,000 Kelvin. Explain. I think I said that. It's basically got to do with the density of states and how it's got to do with this figure, but how this curves change. So basically you get this additional component to the density of states when you get to above 1,000, and that ends up making the heat capacity of the graphite match the diamond. I guess it's higher, but anyway, I think if you figure out from that equation we did, like density of states even in here, right? Somewhere it's like integral of density of states someplace. So you could almost just yeah, it's going to be U. So it's the derivative. Anyway, the density of states is going to be kind of, so it's the integral of the density of states times some other stuff, but basically, like, because the density of states changes with yeah, with no temperature. So density, the point is, like at 1,000, this number, this thing, that integral, that thing changes. So he's got plotted this density of states. I mean, it's not this function, it's the actual density of states. This is calculated from that simple model, but basically there's an actual density of states. So you'd still do the same integral, weighted with the Boltzmann factor. So it will shift things a little bit, but basically at high temperature. So at high temperature, this gets small. So this, I don't know what happens at high temperature. This gets small, so this becomes one plus that energy thing, and the one cancels. You just get that energy thing here. So divided by h nu, it's h nu there, so that cancels. So you have h nu over kt, so it's going to be kt times the density that you're seeing, the integral of that. So when the temperature goes up, that'll even weight it more. So it weights the high end of the density states even more at higher temperature. So anyway, so you can kind of, so that gives you this, and then the change in this with temperature is kind of what you want. So you could kind of use that and just mess around with it and kind of just say what's going on if you want. What's the question again? It's just like, why does that change? So why does the heat capacity change like that? So it's basically because of density of states. You give a short answer or a long answer. Derive 3, that's what I just did, even though I couldn't do the last part. How does it differ from 2? 2 is it's weird that it's an Einstein equation, right? That this W thing, the equation before 2, or does it say actually how does it differ from 2? Just the text before 2. So this is actually the Einstein equation. So that's a direct comparison. So there, like for instance, the prefactor is 1 over t squared. This is t cubed. So that's quite a bit different from the prefactor. And then it involves the same W here. Anyway, they're different. Like they're completely different. They have the same function in them, but basically they're quite a bit different. So you could kind of analyze that at length if you wanted to. Like how you compare the Debye and the Einstein function in the context of this is a weighting factor that's used in the Debye function. And then how does it get the Debye temperature? So you got that from this Debye, I guess he got it from the Debye frequency using that same K, what is it? H nu over K. It's the Debye temperature. So if he knows the Debye frequency, oh no, that isn't how he does it though. No, well, how he does it, right? He does this. He calculates CV. So he has his density functional theory. It gives him this. From this, he gets the density of states. From the density of states, he plugs it in. G is the density of states times this weighting function. He does that integral numerically, and then he gets the heat capacity for every temperature. So he has the heat capacity as a function of temperature. And then he takes those heat capacities as a function of temperature, plots them and fits it to this equation and gets what Debye temperature is. So he doesn't calculate the Debye temperature, he fits this function. He says right here, Debye temperature again is determined by fitting equation 3 to the calculation he did in equation 2. It's kind of interesting. And then one way to do it. So he's got those numbers in here somewhere. I think he compares those with the literature numbers for that. So anyway, that's the way this homework looks. Maybe it's, I don't know. Yeah, I think I would this is one of those cases where if you read this paper first, it's gonna help. Like read through it and figure out what's going on, and then go back and just see if you can answer the questions. The first question should be pretty easy. And then this is just from the notes. That should be pretty easy. And then that thing is from the notes. And then this becomes harder as you go on. There's more than 5 questions here. So that even though the first 3 questions are kind of free questions, then you still have 4 more questions that aren't free. So 2, 3, 4, 5, 6, 7. So it's like I don't know what they're worth, like 15 or something each, something like that. So hey, there's kind of short questions, but you should be able to, shouldn't be too bad. I know there's more than 5, but so all right, let's kind of forget about that. Any questions on that thing? Yeah. All right, so let me get back over here. Right, so right, so we got all these things. Did that. I got that. This- Yeah, so there is this parent, like this parent equation for the optical and the acoustic phonons, and there's like two solutions, plus and minus. So it kind of gives the two curves here. But getting that equation's like pretty hard to do. Basically, there is one master equation to get both kinds of vibrations out of a, and those are the functions. I think those might be in the book or something, or maybe they're at this web page, optical something or other. What else? Oh, this is also in that Libra text thing, but basically, so the idea is you get this dispersion relationship. So frequency versus wave vector. And then you need to get the density of states from that to do these kind of integrals, wherever that is. You need this density of states to do the integral to get the energy. Are you going to integrate density of states times the Bose-Einstein times the frequency gives you like the average energy of the thing. Right. So anyway, how do you convert, like the question is, how do you get from this dispersion relation to the density of states? Like, how do you couple those two to get one to the other? In other words, how do these curves tell you how energy is distributed over frequency? You have wave number and frequency, and somehow you get right. So anyway, the only thing I could find that directly did that was like this thing from this Libra text thing where they did that. So that even that is kind of or relating wave number and frequency when you just say that. That's already a relationship. So let's see, how do you do this? Oh, okay. So then you have to just, it's just, I guess you need to apply to the dispersion relation you have periodic boundary conditions or some kind of boundary conditions. And then you can solve, once you have that, you can solve for like how energy is distributed over the, this doesn't seem to answer that question. Yeah, let's see. Does this thing do it? I guess I still don't see exactly how you get from one to the other. Not straightforward. It's in here. It kind of says that it does it here, but it doesn't really do it as far as I can see. I'll have to go back through that and figure out what's going on. Did all this stuff. You can, I think in our book, oh no, this is from Wikipedia too. So they calculate, so you can get a function for the Debye and the Einstein, and you can get actually a relationship between the Einstein temperature, which is kind of like a mean frequency, and the Debye temperature, which is the absolute smallest or highest energy absorption, right? So Debye has to be larger than Einstein because that's the maximum and that's the mean. And then you end up with this 0.8 that relate the two, which agrees with like kind of the literature for it. So it's possible to calculate that. Then what else? We did that already. Oh, it says in this paper too that the stronger bonds have a higher by temperature. But this is for buckyballs, graphite, diamond. And I guess the bonds go weak, stronger, strongest, something like that. So anyway, or yeah, so the higher the by temperature is higher bond strength or something. The graphite is lower because it's just sheets sliding against each other. In plane strength is higher, like it says in that paper, but basically this is for the sheet sliding thing. The buckyball has a lot of like kind of breathing vibrations to it, so like it oscillates like that, like a volleyball when you hit it, kind of thing. So I think that's why that temperature is so low. That's pretty low. 46 is a pretty low temperature for that. That's a plot of all the Debye temperatures, and this gamma is the electronic contribution number for this thing, which I think is, oh, this is just going across bond strength. You get a higher Debye temperature with stronger bonds. These are ionic bonds. And then, oh, this is the calculation of the modulus for the homework. This is actually the whole thing. So once you get all right, so how do you get the modulus here? K is a newtons per meter. Shouldn't it be newtons per meter squared? And this should be per meter squared, I think. All right, there's the Debye temperature, 344. Oh, and then you can calculate the Debye frequency, 32 terahertz. And then what do you do? Oh, the frequency is K times M, you know, the mass of the, whatever this is, copper. Then you can get K from that. K comes out to be this number. And then you need another size. I guess it would be the size of the lattice spacing, like the A for the crystal. In order to get modulus from that, it would have to be Newton per meter squared, right? So I think there's a lattice spacing missing in this. I think you need to divide by lattice spacing in this thing. But that would be a really small number, so I'll give you a huge. Anyway, this is kind of says how to get the modulus, how to calculate the modulus from it. So once you have the modulus, you can go back and calculate the Debye temperature. This is from the book. It compares like the heat capacity, kind of fitting the heat capacity versus temperature to get the Debye temperature, and then just calculating it from the modulus using something like what's going on here. So the numbers are almost the same. The difference is due to the optical vibrations. Right, so you'd expect to see more difference for the salts, like the polar compounds. So there's like a 1-2 degree difference, I guess. And then these are closer. I think these should be closer theoretically. Like there's not really optical vibrations for a metal crystal. So yeah, why don't I can just finish this off. Let's see, we've got a lot of other slides in here, right? Yeah, I'm gonna have to do spectroscopy. We can do, there's a Brillouin scattering setup downstairs in Rhodes Hall, so we could kind of look at that if you guys want. But the problem is it would have to be at 3 o'clock, not today, but like have to arrange it. But if you want to do that, Nichols has it. It's down on the 4th floor in Rhodes, the end of the hall. It's kind of interesting. I mean, it's pretty elaborate kind of setup. So Well, we could do that, but it would have to be at 3 o'clock, maybe I'll email him and see when he can do it. Cause I have that other class, so it'd have to be like after that, but. Anyway, so I want to go through the spectroscopy things. Oh yeah, calculate the entropy. So there's a lot, there's enough for next week probably here. Group contribution. The electronic thing, I'll have to go through that. And magnetic heat capacity we need to do. And then transitions. Yeah, there's quite a bit to do. There's a week worth of stuff in here. There's something about polymer heat capacity too. Oh, glasses. Yeah, there's a lot of things in this chapter. So we'll probably do this like next week. There's enough stuff here. I'm gonna quit there, I guess, for today. This is something else going on, but